My name is Lee Katz, and it is my privilege to serve as the interim dean of Seaver College and welcome you to the first W. David Baird lecture series in this 2023-24 year. This lecture series was started in 2002 by David Baird, who served for a decade as the dean of Seaver College. A renowned scholar and historian, Dr. Baird authored over 10 books and 27 journal articles about the history of Native Americans and the West throughout his academic career. He created this lecture series in an effort to help fulfill Seaver College's mission, which aims at enhancing our students' ability to think critically and about a broad range of subjects. As a result, each year we bring to campus experts and thinkers from a variety of fields to tell us about their work and its implications. Hopefully, in doing so, our community is challenged to consider something new, and they are inspired to confront that which is unknown. I think for many of us, dark matter falls in that category of the unknown. As we embark upon this goal tonight, it is an honor to have Pepperdine University's own Associate Professor of Physics, John Mann, here to introduce our esteemed speaker. Professor Mann has been a member of the Seaver College faculty for the past 9 years, an esteemed researcher himself. Last summer, Dr. Mann was the recipient of a cross-disciplinary undergraduate research grant, which allowed him to blend the study of physics with intercultural competence as he helped develop Pepperdine's University Robotics Club and their autonomous racing competition. I want to attend that. John holds graduate degrees in both physics and materials science, which he earned at the University of California, Riverside, which is also the home institution of our esteemed speaker tonight. Before beginning this evening's program, I want to recognize a couple guests, President Gash and Jolene. Thank you so much for being here. Provost Brewster, let's thank them for being part of our event. And a quick note about tonight's format. Following our speaker's address, we will take a brief 2 to 3 minute recess to excuse students who have to attend evening classes. If you don't have to, often you know that the question and answer time is sometimes the best, most interesting time for these events. So if you don't have a class, please stay and attend that question and answer. And after the lecture, we will be able to thank Dr. Tanedo for his presentation. So at this time, please welcome Professor John Mann.
Not used to being the short one here. So it's with great pleasure that I get to introduce Philip Flip Tanedo. I'm personally really excited to hear his talk. It's about one of the fundamental unresolved questions in astrophysics and cosmology, namely, where's the dark matter? Professor Tanedo's research efforts seek to answer this question and determine the fundamental physics of dark matter. I would like to tell you a little bit about our distinguished speaker. He has degrees from some of the most prestigious research institutions in the world, including a bachelor's degree in physics and math with honors and distinction from Stanford, not a bad university, graduate degrees in physics from Durham and Cornell, and he did his postdoc at the University of California, Irvine, where he was a Chancellor's Advanced Postdoctoral Fellow. He is currently an associate professor at the University of California, Riverside. In addition to his affiliation with prestigious universities, Professor Tanedo is a recipient of many awards and honors, including being a Marshall Scholar, a Paul and Daisy Soros American Fellow, a Hellman Fellow, and a National Science Foundation Career Award winner. Additionally, he was recently appointed as a member of the High Energy Physics Advisory Panel of the NSF and Department of Energy. Now, of course, these many academic achievements don't tell his whole story. He's also involved in scientific outreach and has appeared in Nova, Science Friday, Radiolab, and Ologies, one of my favorite podcasts. He's an advocate for equity in academia and has led UCR's team in the American Physical Society's Inclusion, Diversity, and Equity Alliance. Professor Tanedo is a Southern California local who grew up in Los Angeles and is the first Filipino-American professor of physics. Please join me in welcoming Professor Tanedo to Pepperdine.
Thank you for that really kind introduction. So, my name is Flip Tanedo, and I am a theoretical physicist. If you ever find yourself on a plane with a nosy neighbor, one thing I found is if you want to buy yourself a quiet flight, I am a theoretical physicist is a pretty good way to do it. So, I study dark matter, and dark matter is this big puzzle that we'll learn a little bit about tonight. If I knew what it was, this talk would be very different. So instead, we'll talk a little bit about dark matter, but really talk about what it means and peel back the layers of what it means to be a theoretical physicist studying dark matter. And like any good detective novel, there's a who, what, when, where, and why, and a how. And that's how we're going to proceed, not necessarily in that order. Let's start over here with the what. So the main character of our story is dark matter. Dark matter is invisible, and if you'll permit me some artistic impressionism, it looks something like this. Let's see if I can move the mouse. Let's get the mouse out of here. This is the Milky Way. We live there, and we live in a bubble of dark matter. This bubble is more like an ocean of dark matter. And if we were to zoom out a little bit more, again, forgive me my artistic impressionism, we would see that our bubble of dark matter is one of many bubbles of dark matter. And if we squinted, which you can't see here, we'd see that these other bubbles of dark matter each happen to have their own little galaxies. And we'd see that this group of bubbles of dark matter also seem to be replicated in other parts of the universe. So we are not only just one galaxy in a bubble of dark matter, in a group of bubbles of dark matter, there are other groups of bubbles of dark matter all over the place. In fact, one could say we are swimming in an ocean of dark matter. This bubble is an ocean, and what we really are fish who, for the first time in fish history, are discovering what the heck water is. And there's something deeply significant about that. Are there any physics majors in the room? Okay, very good. So here's where we're going to start. We are all going to assume that dark matter exists, and the one thing that we know is more or less how much dark matter there is. Everyone on this side of the room on board? Right? The humanists are like, yeah, okay, that sounds good. The physicists, I hope, are deeply unsatisfied. Do not tell me what there is without evidence. Good. We know that dark matter exists, mainly because astronomers tell us so. And there is all sorts of evidence coming from the motion of stars in galaxies to the motion of clusters of galaxies that appear to be pancaking onto each other to something called the cosmic microwave background, an imprint left 13 billion years ago that our telescopes can now see and study in this fuzz some patterns that reflect the indelible presence of the gravitational effects of dark matter. By looking at things that are visible, we have indirectly found that there is more stuff than the 15% of the matter of the universe that is made up of protons, neutrons, electrons, and their various reconfigurations. Okay, that's pretty good. Physicists in the room, you guys are convinced? Now, it's actually better than this. So this is a slide from Katie Mack, a fantastic physicist at Perimeter Institute, where she listed her 12 favorite, most compelling reasons why we believe dark matter exists. And the physics people, you can write this down. There's a quiz. All of these come from the sky. All of these come from indirect evidence of the gravitational effects of things that we cannot see. So what I want to impress upon you, when I'm telling you, let's all be on the same page, and let's just start with dark matter exists. It is not just that it walks like a duck and talks like a duck. All right? All of this is data from different times, different places, different parts of the cosmos and the cosmic history. It walks like a duck, it talks like a duck, it has feathers, it left duck poop, and guess what? It has duck DNA. That is how compelling the evidence is that there is particle dark matter. Any philosophers in the room? Usually around here, this philosopher will say, well, you could still be wrong. Which is true. And there's something important about this. We are being extremely conservative, even with this huge array of evidence that there is something missing and it's a particle. We could be wrong. We're just applying Occam's razor. If we were wrong, that would be amazing. It'll be raining Nobel Prizes. We'd be rewriting our textbooks, and that is good. That is exciting. We are learning something deeper. So what we are doing is we're being extremely conservative and saying, based on what we see, let's take the most conservative approach, do the least to our theories, and see what it predicts. All of this is coming from astronomy. You might have noted, I am not an astronomer. My astronomy colleagues would kill me if I said that. I'm a particle physicist. So that ties curiously into this question of when. When what? Why are we studying dark matter now? So let me give you an incredibly opinionated, more or less correct history of dark matter. Don't hold me to this. What you see here is a timeline that is the confluence of two very different branches of physics. On the top, you have particle physics, the physics of the very small. Our tools are microscopes, and by microscope, I mean particle colliders that probe the smallest subatomic length scales. On the bottom, you have astronomy. Their tools are telescopes. They probe very big things. And what's really curious is, here we are approaching today, we're basically doing the same thing. Now, my very biased, semi-accurate version of dark matter history is that 90 years ago, people like Oort and Zwicky, shown over here, found the first evidence that there is missing mass in the cosmos. They were looking at clusters of galaxies or something like this. And at the time, the 1930s, the observation that these brand new telescopes looking at these faraway objects for the first time see something kind of strange, maybe you're not so surprised. Oh, maybe the telescope wasn't polished. Maybe you don't understand the foreground and the background. Oh, okay, so there's some curiosity. And that was the status of things for maybe a few decades before Vera Rubin. Vera Rubin took spectrographic measurements of the motion of stars in spiral galaxies. So spiral galaxies are the galaxies that look like our galaxy. And she found strong evidence that indeed, in a completely different system, so in individual galaxies rather than clumps of galaxies, there is missing matter. If you just looked at the stars and tabulated what the mass of those stars ought to be and looked at their motions following Newtonian physics, it didn't work out. The math didn't work out. It really looks like there is missing matter. That's super exciting. And if the missing matter isn't the stuff that stars are made of, then the people whose job it is to understand the fundamental building blocks of nature should be really excited, right? So if you were a particle physicist in the 1970s and had nothing better to do, there's a big caveat, you would drop everything and try to figure out what this missing matter was. Okay. Now, on the top part of this timeline is particle physics, and I'm only showing three dudes over here, but there's a long history that over these decades, these particle physicists had just built their brand new shiny toys, which were early particle colliders, and they were seeing a cornucopia of new particles. And the big exciting thing was, how do we make sense of all of these new particles that we're producing? And the inflection point here that I'm going to show, is the Nobel Prize in 1979 by Glashow, Weinberg, and Abdus Salam. So I believe Abdus Salam was the first Muslim scientist to win a Nobel Prize. They won the Nobel Prize for the invention of what is now known, or at least the core of what is now known, as the Standard Model of Particle Physics. This was the mathematical description of subatomic physics that described all of the particles that I'm not even going to show, but were in the decades before. And over the next 3 decades, successfully described every new particle that we discovered by augmenting them into the existing theoretical framework. It was a big deal, a capital B big deal. And the one thing that was missing from the particle physics timeline, the one thing is that the particle physicists had an idea but did not yet confirm where other particles got their mass. There was an idea. The idea is something called the Higgs boson. How many people here have heard about the Higgs boson? Ooh, much more than the number of physics students. Very good. Okay, so we knew about the need for the Higgs boson, or something like it, this magical ingredient that seems to give mass to particles, which is kind of an important thing, right? And it wasn't until the 2000s that we completed the Large Hadron Collider, and I suspect the reason why many of you know what the Higgs boson is, in the 2010s we discovered the Higgs boson. And it wasn't until around the 2010s that the particle physics community really tilted and realized there's this other puzzle that I've been hearing in the back of my ears. It's almost as if the astronomy department's been talking about it for decades. And it's not until the 2010s that people really shifted towards dark matter. All right, so that's the approved for a general audience version of the story. Here's a slightly different version. Let's zoom into particle physics. This is the standard model of particle physics. I don't expect it means much by itself, but the first thing you should see is this is a table. Like the periodic table. Okay, I've seen the periodic table. And it's a table where every row is a type of particle, and every column is a property of that particle. So the particles have funny names. This column over here tells you whether the particle is more like a force particle or a matter particle. And these 3 columns, with their funny symbols, tell you how each of these particles interact with respect to the 3 fundamental subatomic forces. Right, so now my grad students get to have the gory detail of how to convert this into calculating actual things in an experiment. But what's important for us here is that there is a table. That means, even without knowing the details of the elegant mathematics behind this, if I told you there's a new particle, you already know, okay, there's a particle. It should either be matter-like or force-like. There should be some weird symbol over here telling us how it interacts under the force that holds the proton together. And there should be some numbers over here that tell us about how this particle interacts with light. There's an organizing principle. The beauty of the periodic table of chemistry is not that we have a list. The beauty of the periodic table of chemistry is that there is an organizing principle behind it, and that's quantum mechanics, the quantum mechanics of atoms. And the magic, the beauty, the elegance of the standard model of particle physics is that there is this organizing principle behind all of this. Okay, so the status was this row here had not been discovered, but it plays a critical role in the theory. Okay, so let's be radically conservative again. It would be amazing if there were no Higgs, because then this missing ingredient, something else has to fill in the void. And something crazy would happen if we collided particles at a certain energy. That would be amazing. We would love that. Okay, what's the conservative option? There is a Higgs. It turns out there is still a puzzle. This Higgs, which gives mass to the other particles, there would be a puzzle about the mass of the Higgs itself. And the puzzle is that when you calculate the mass of this hypothetical at the time particle, it's the balance of two numbers, like a seesaw. And these two numbers have no reason to be related to each other, but in order for all these things to work out, those two numbers have to be basically equal to a really fine degree. And theoretical physicists love puzzles. And so they said, well, even in this conservative case, we have a puzzle to explain. So here's the playing field. By this time, maybe 50, 60, 70 years of astronomers saying, hey, particle physics dude, we're missing some matter. There should be some new particles. And the particle physicists just cared about, we have this elegant mathematical theory that will tell us everything about subatomic physics, and we're really looking for this one particle, the Higgs, and understanding why the Higgs is light. And that is more important than this dinky other particle that you're talking about, and these are all from telescopes anyway, so how much can we really trust them? Right, so the hubris of theorists. So what happened were some of the most elegant, beautiful, and ultimately wrong ideas in particle physics. And let's go through how that worked. Here's idea number one, supersymmetry. My first paper as a grad student. Sorry, this is actually a much more personal story than you might appreciate. So we start with the problem the particle physicists cared about. The Higgs mass. What is the mass of the Higgs? Up here in the top left. And they came up with this, truly beautiful, elegant idea called supersymmetry. In a nutshell, supersymmetry is a symmetry between matter particles and force particles. If you have a matter particle like an electron, you have a force particle, which has a silly name called the selectron, because you put the S because it's supersymmetry. Okay, it turns out that when you impose this additional mathematical structure, you end up solving the problem of two numbers having to cancel each other out. Great. Excellent. So what? Well, it turns out that if you have this new symmetry, and the symmetry says every type of particle you have a matter particle gives you a force particle, every force particle gives you a matter particle, you end up with a boatload of more particles. Okay, so our theory predicts more particles. There's a theme here. It's mo particles, mo problems. What happens is, so some of you are already thinking, more particles. Didn't I hear that before from some astronomer? Good. But again, particle physicists didn't care about the astronomers' problems. The bigger problem was you put in these new particles, and they cause protons to decay rapidly. That's pretty bad. Protons, to the best of our knowledge, are stable. Experimentally, we know they live for at least 10 to the 32 years, which, by the way, is older than the age of the universe. So physicists should figure out, how do we know something is aged longer, lives longer than the age of the universe? So the fact that these new particles induce rapid proton decay is clearly inconsistent with any observation of anything. There is stuff rather than no stuff. So what do? We pout because our beautiful idea wasn't just exactly right from the get-go. And then we think, and then we say, well, maybe the universe is not a beautiful, elegant place. So we put in a hack. We tweak the theory. We have beautiful, elegant, wonderful, deep mathematical insight. And then ugly little thing. It's like you're going to the used car salesman. You're like, oh, I'm buying a new car. Well, let me upsell you with this additional warranty. Right? It's a little thing you tack on just to make things work out. So this thing was called R parity. I cannot tell you what R stands for. I don't know, and to be honest, I don't care. But this R parity was a different kind of little tiny symmetry, tweaked the theory in a funny way. Okay, so what? It turns out that doing this little tweak introduces a conserved charge in the theory. So, for example, electrons have charge. Electrons don't decay because they're the lightest particle that carries that charge, and they have nothing to decay into to pass that charge onto. And so what the result is, you have new particles. The lightest such particle that carries the new charge that you had to put in to make protons stable, the lightest such particle is now stable, cosmologically. oh, now the ingredients are really interesting. Not only do I have a boatload of new particles, but some of those particles are cosmologically stable and should still be around in the universe today. Huh. And now the particle physicists remember, oh yeah, the astronomer downstairs was saying something about this the other day. There was one calculation to do, one big one. You predict that there is stuff. The stuff is cosmologically stable. What was the one thing that we knew about dark matter? We know that it exists, and we know roughly how much there is. So we proceed to do a calculation. Every particle physics grad student at some point does this. And the calculation is tricky. You take the properties of these new particles from this deep, elegant, blah, 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 blah theory. Then you compare the production of those particles in the early universe, this hot group of plasma, to the expansion of the universe, which is this weird general relativity Einsteinian thing. And you crunch the numbers, and wouldn't you know it, it turns out that you get the right abundance within an order of magnitude or two. Okay, so the chemists, of course, are laughing. The chemists are like, order of magnitude. In this business, 2 orders of magnitude, ballpark, is amazing. In fact, there are people who called this a miracle. And when you step back and look at it, you realize, well, the structure, this logical structure here, was that we put in a deep, elegant, blah, 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 blah symmetry, which meant all of these new particles inherited their properties from the Higgs. And when you crunch the numbers, it just so happens that the typical masses that you get and the typical interaction strengths that you get end up giving you just what you need to produce the correct abundance of dark matter that we see today. Cool. Maybe that's amazing evidence that this is it. So you celebrate. You go to the bar, you start planning your next big collider, you have a good time, and then you wake up the next morning or the next week or the next semester, whatever it is, and then someone knocks on your door. Professor, I just read your paper about dark matter and supersymmetry. Wonderful work. I'm a first-year graduate student. I'd love to work with you. What's my first project? Oh, okay. Spent a lot of time on this. This was pretty good story. But you think, okay, let's try something else. Maybe we need another deep, elegant mathematical reason why the Higgs is light. My clicky isn't working. Is there a... So maybe there is a different reason why the Higgs is light. And you come up with something new. Oh, thank you. Thank you. So you come up with something new. You extend space-time, extra dimensions, weird sci-fi fun stuff. Okay, you figure out the mathematics. What does it do? Well, if you have an extra dimension, the ways that particles can rotate in the extra dimension end up manifesting themselves in the ordinary 3 + 1 dimensions in a certain way. How? New particles. Oh, okay, well, mo particles, mo problems. So there are new particles from extra dimensions, and stop me if you've heard this before. Now those are in conflict with other types of experimental observations. These are called precision observations. You take certain types of heavy particles, you watch how they decay, you measure things. Numbers have to work out. And they don't because these damn new particles end up screwing everything up. Oh, shoot. Deep, elegant theory. Oh, wait, we've done this before. I just have to invent a little tiny hack, just a modest little thing that we just tack on, slide it under the rug, something called KK parity. Okay, what does that do? Well, it prohibits the interactions that are bad, that cause things to decay too fast. But it also gives you conserved charge. Oh, conserved charge. If you have a conserved charge and new particles, then the lightest particle with the conserved charge is now cosmologically stable. And now you think, oh, okay. You go to the grad student, please calculate the abundance of these cosmologically stable new particles that we predict from this completely different theory. Now, in the back of your mind, you know that the masses of the new particles and the properties of the new particles are all still inherited from the Higgs. So even though the details of the mathematics are slightly different, you know they're going to end up with a ballpark of the correct amount of dark matter. The grad student's ecstatic, graduates with a PhD. You celebrate. Whew, dodged a bullet there. We got to use the same pipeline. Next morning, Professor, I saw your paper on extra dimensions and supersymmetry. Great work. I'd love to be your student. What's my first project? Holy moly. Okay, so maybe the Higgs is light for some other, maybe it's composite. So this is the idea that the Higgs is not a fundamental particle, it's a bound state of two other particles. So what? If two particles can be bound in a certain way, they can form other types of particles. What does that look like? More particles. More particles means what? Oh, those new particles induce new interactions that violate known observations. And you're seeing the rise and fall. The grad student, like clockwork, you can see the grad students' hopes go up and then down and up. And you say, what if you introduce a new parity? Oh, really? What's it called? T parity. What does T stand for? I don't care. What does it do? It introduces some conserved charge. It prevents all of the processes that violate these things. Meanwhile, of your new particles, the lightest such particle is now cosmologically stable. Oh, could that be the dark matter? You know what you should do? You should do the calculation of what's the cosmological abundance of this new particle. Oh, yeah, I'll do that. The next morning, Professor, did you know? I'm pretty sure you got the exact number that we predicted. And it's not a surprise. Each time it looks like some miraculous thing, but you realize it's just that the numbers associated with the Higgs boson, when you apply this game of putting some deep symmetry that introduces new particles that all inherit those properties, there was one miracle that it happened to give you the amount of dark matter that we actually see. Very good. Then you go on sabbatical, so no more grad students are knocking on your door. Meanwhile, you step back and you look at your picture of theoretical physics. We've been talking about we need to find this particle because when you find that, either you don't find it and something amazing happens, right? Let's be clear, that is the most amazing situation. Or you do find it, and then you have a puzzle. Why is this thing like this balance of two numbers? But you now have three amazing solutions that tie the balance of these two numbers to deep mathematical truths about the universe. You're in a pretty good spot. This is a no-lose scenario. If you don't find the Higgs boson, amazing. If you do find the Higgs boson, there's a puzzle. And guess who wrote the first 3 papers on solving that puzzle? Great. It's a no-lose scenario. So 1990s, this is what the standard model looked like to theoretical physicists. This is what experimental physicists look like to theoretical physicists. And I'm joking, of course. What's amazing, though, is very rapidly, the moment that you had a no-lose scenario, you build this collider, we will see what comes out, and whatever comes out will be amazing. You go very quickly from this to this. And within a few years, which is amazing, you go from that to that. So it's now September 12th, 2023. Within a month, we are a decade from the Nobel Prize for the Higgs boson. People remember that? Some of you in the room? How many people remember, so this was Peter Higgs and company, how many people remember the person who won the Nobel Prize for supersymmetry? Or extra dimensions? Or compositeness? Or any of the other cockamamie ideas that we had that were deep and elegant and meaningful? No? History students? That's right. There were no Nobel Prizes because there were no new particles. Huh. Ain't that a mess? So in 2013, I was writing up my dissertation on a bunch of ideas on, wouldn't you guess, supersymmetry, extra dimensions, composite Higgs, and all of the wonderful things you would see at the Large Hadron Collider. And I was interviewed by Science News, and inadvertently, this is an actual photo spread from the magazine, inadvertently I became the poster boy for the ennui in the field. Because we had just promoted for ourselves this idea that we couldn't lose. And indeed, Peter Higgs did great from the past 10 years. Peter Higgs walked away with the Nobel Prize, vindicated. But here was a generation of theoretical physicists who were expecting to be working on classifying all these supersymmetric particles, and we found nothing. All right. So maybe this love story between the Higgs and dark matter, this wonderful miracle where the numbers just work out, this had to be right. Maybe it was time for a breakup. And that's why in 2013, a big fraction of the theoretical physics community realized, you know what? Dark matter is a really interesting problem. And it's not just the ennui or the personal story of what do we do next. It was something where there was a group of people who were talented and trained in how do you modify this model of particle physics? How do you play with a mathematical theory to bend it, to cheat, to see loopholes, to create new things? And that's exactly what we need to study dark matter. But even more than that, we still had this. We still have the premier microscope, the highest energy particle collider in all of humanity. And not only that, because we were confident about what we were going to see, we also have things like this. This is LUX. This is one of the most pristine underground environments to study the possible ephemeral interactions of dark matter on nuclei. And even without dark matter, but something which could be used for dark matter, our friends in the astronomy department weren't just sitting on their hands. They went on and built amazing telescope arrays like this, CMB Stage 4 in the Atacama Desert in Chile, which will probe the cosmic microwave background formed 13 billion years ago, on whose fingerprints we hope to see details of the ways in which dark matter affected the cosmic plasma. And in just the last 8 years, we have opened up a brand new way of seeing the universe through gravitational waves, the very ripples of space-time itself. So don't cry for me because my PhD is now stuck in the bottom of some library trash bin. This is the time to study dark matter because we have all of the tools to do it. So I'm a big NBA fan. One of the big things from Twitter in the past couple of days is LeBron James said, I'm going to recruit all the NBA superstars to play for the Olympic team. You know, it's like LeBron James was recruiting the Avengers. That's what this feels like. It's like all hands on deck, physical science. We have the tools to have a spitting chance at understanding dark matter. That's why now is the time. Okay. Every 10 years, the particle physics community has a decadal survey where we study and we come together and we agree upon what are the key science drivers for our field. How do we prioritize our resources to figure out how to maximize our discovery potential? And this process completed recently, and this is a picture of some of the people who attended, and it's no surprise that dark matter was one of the key science drivers. Okay. Let's jump into how. One of my favorite questions that I get is, you're a theoretical physicist. Does that mean you theoretically do science? Like, what do? You got an armchair? What is that? You have no lab? I have no lab. I don't have an armchair. I do have a chalkboard, a nice laptop, lots of paper, a fancy pen, and a garbage can. What I do the most, though, is I talk to other physicists, and we talk about physics. And that's the most valuable thing. So let's talk about theoretical physics. First of all, what is a theory in particle physics? It's not like in chemistry where a theory is something which is like, this is the law. Theories in particle physics are models. So on the left is one picture of the standard model. On the right is literally another picture in a slightly different language. For the physics people in the room, this object here is a Lagrangian, which you might remember from analytical mechanics. These models are written in a language. The language is called quantum field theory. It's like the bigger cousin of quantum mechanics. And that mathematical language, quantum field theory, imposes an internal mathematical consistency on your theory. That means I can add rows to this table, I can maybe imagine new forces, I can play with these things, but there are rules. It's not just the Wild West. And being able to play with those rules and see when you can get around them, that's the game. So there's an example of this. How many people know about the discovery of Neptune? Few people. Okay, so that's not bad because usually when I talk to particle physicists, I say, do you know about the discovery of Neptune? And they say, what the heck is Neptune? Is that a new particle? So Neptune is a planet, and it was discovered, we credit this guy, Urbain Le Verrier, a French physicist / mathematician. There's no difference back in the 1800s. Urbain Le Verrier would look at these astronomical tables. This is basically positions of planets in the sky every night. And he would use the theoretical tool of the day, Newtonian gravity, to calculate where those planets ought to be and compare them to what he saw the next evening. And there was a puzzle. The positions of Mercury and Uranus were off every single time. And he said, oh, geez, well, what's happening here? I can be conservative, and I'm going to assume that Newtonian mechanics is correct. The Newtonian potential coming from these planets moving around, da-da-da-da-da-da. Maybe there's a missing planet. That's like adding a new row on that table. Maybe there's a missing planet. And he calculated what the mass of that planet had to be and what the position of that missing planet had to be to explain the motions of the planets that he did see. Right? The analogy to dark matter, I hope, is clear. And wouldn't you know it, so his prediction was over here in the red circle. The observation was here in the blue circle. And because this is sometimes the way science goes, he had an English rival, because that's France and England in the 1800s, who had made a different prediction. And because his prediction was closer, we say Leverrier discovered Neptune. But using theory, using mathematics, he wasn't the one on the telescope. Cool. That sounds like what we're doing. And in fact, a little bit later on, there was another puzzle called the precession of the perihelion of Mercury. Anybody know this story? Okay, the physics people will love this. The precession of the perihelion of Mercury, the perihelion of an orbit is the position of closest approach to the sun. The precession of the perihelion means that the trajectory of Mercury looks something like a spirograph, which I know the students here don't know what a spirograph is. It's what we did before we had the internet. The puzzle was, we don't know why the trajectory of Mercury had this really funny spirograph shape. And Urbain, who had developed some self-confidence, had said, I know what this is. There's another planet. Let me calculate. Yep. I'm going to call it Vulcan. I don't know if he called it Vulcan. But here on this map from 1846, it's called Vulcan. It's close to the sun, and it explains why Mercury should have this funny orbit. Is there a planet Vulcan? Only in Star Trek, and it's certainly not in the solar system. Not in our solar system. So what happened? This approach of radical conservatism ended up being wrong because, I don't know, 70 years later, the precession of the perihelion of Mercury ended up being one of the key early pieces of evidence for the theory of general relativity, a deeper, more unified theory of gravitation. Okay, so we'll go from Star Trek to Star Wars. This is a really important part. What's the difference between these two pictures? They're both the Millennium Falcon.
One's Lego and one's like...
Brilliant. I will take you as a graduate student. Brilliant. So this is a picture of the Millennium Falcon, presumably from one of the movies. And this is a picture of a Lego set of the Millennium Falcon. One is the actual thing. The other is a model. Rule number 1 of theoretical physics. You never confuse the model for the thing. And this is the thing that we as physicists often get accused of. A model of nature is not the same thing as nature. If you zoom in, you realize this thing doesn't quite work out. When we write down our quantum field theories, no honest physicist is actually saying, I am going to impose upon this universe that this is the way you're going to work. What we're actually doing is, I am going to build a theory that I can use. That means I'm making simplifications, approximations. I'm using the building blocks that I have. Associated with those building blocks is an understanding that if I look too closely, things won't work out. And that's okay, as long as my theory is correct or approximately correct in the region where it should work out. Any good theory knows where it's going to break down. And what you're looking for are deviations from the regime where you expect it to work. Okay? Do not confuse the model for nature, which might shed insights about deep principles, but that model is not nature. All right? There's a great piece of surrealist, I think it's surrealist, Dadaist art called The Treachery of Images by Magritte. This phrase over here says, this is not a pipe. What? Well, of course it's not a pipe. This is a picture of a pipe. It's a representation of a pipe. In the same way, this standard model is not nature. It is a representation of nature. It's an approximation of nature. It's a mathematical model of nature upon which I can make predictions, and to some regime, I cannot make predictions. So when we talk about how do you do theoretical physics, this is usually what it's like. Right, so take notes, because this is what your grad school is going to be like. There's a puzzle. The puzzle is always relative to some known existing information, usually data. And it's a puzzle because your theory doesn't seem to fit both the new thing and the thing that you've established. So what do? And this should start sounding familiar. You make it fit. It doesn't have to be pretty. You just pull out whatever block you need to, and you hammer it in, and you put glue, whatever you need to do. And you have a Frankenstein model, not elegant, not the thing that you would be necessarily proud of, but you learn something. You learn that, oh, when I put this hack in, the reason why it makes these two things fit together is because it introduces this new conserved charge and blah, 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 blah. You learn something about what it takes to make your model better fit with data. And having learned something about why your model can fit better, maybe someone else will come over and she might tell you, hey, you know what? I actually have another model built on some other deep mathematical, elegant, blah, 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 blah idea. And when you put that idea into quantum field theory, not only does it have the feature that you had to hammer in, but it has it for free. Oh, and this is now like improv, yes, and it has some other prediction. And now in order to test whether this new extended model has validity, you check that prediction. You go back to your experimental colleagues. That is how theoretical physicists earn their stripes. You don't have to do all three of these, but you have to do at least one reasonably well. Okay? I'll say one last time. The critical thing in this whole endeavor, I'm on the theoretical side, but the critical thing is that all of this is really firmly based on experimental science. Okay. So here's a funny question. Who? Let's zoom back out. Who gets to play this game? Who gets to be on this endeavor? And there's an analogy here, right? Dark matter is not dark. It is invisible. And it's kind of a tortured analogy. Many people have made this. But ordinary matter, which is 15% of the mass of the universe, has the privilege of being charged under electromagnetism. Right? Electromagnetism is a tool by which we actually probe everything in our laboratories. Everything is, in ordinary chemistry, is electromagnetism. Meanwhile, there is this whole bunch of other stuff, 5 times more other stuff, which in fact is more responsible for our cosmic origins and our cosmic destiny, that just happens to not have that charge. And, okay, you can go on with this analogy. The analogy gets more and more tortured. But there are many, many books by intelligent people, and I recommend all of these, talking about the people who do and do not get to participate in the scientific endeavor. And this is like the dark matter problem. It's not that there's not enough data, right? The astronomers were telling us for 90 years that there's missing mass. It's not that we don't have data, right? There are demographics, both visible, like race and gender, and invisible, like privilege and class and socioeconomic status, that are not accurately reflected in the scientific endeavor. And it turns out physics seems to be particularly behind the times. This is a complicated problem. If I knew what the answer was, I would tell you. I'm sorry that I don't. Honestly, I am sorry that I don't. It is a subtle problem. But let me focus on one aspect of this. And the one aspect that I often hear from very well-meaning and very reasonable people is Maxwell's equations do not care about your demographic privilege. And that is absolutely right. Whether or not dark matter exists or the laws of physics or what Lagrangian there is for the universe, it doesn't matter who the person is who is discovering those laws. That is absolutely true. But the act of doing science is an intrinsically human thing. And more often than not, the well-meaning but young people who say this early in their careers often find themselves thinking, and sometimes saying out loud, things like this. Oh, if only I had been at this prestigious East Coast institution, I would have had the letter of recommendation from this well-known person that would have gotten my career launched in a certain way. Oh, if only I had taken this amazing summer program where I could take calculus as a, junior high student, rather than being in this particular public school where by the time I entered freshman physics, I was so far behind in math I couldn't complete the program in 4 years. Or when I face adversity, which any meaningful human endeavor, you will face adversity. If you're the one in the classroom raising your hand and you realize your hand's the only hand of that color, do you feel like, hey, this is an opportunity to shine? Or do you question why you're in the room? And again, these are incredibly subtle problems. They're challenging. There is a problem. It is not acceptable to do nothing. But what's also true is, with all the well-meaning in the world, doing the wrong thing could be worse than doing nothing. But this is the problem that we need to solve. What I want to focus on is that the way this problem has been phrased so far, I think is also missing the point. This problem, as phrased this way, has been about, what do I deserve? What type of fair chance do I get when I want to do this thing about me becoming this scientist and me getting this Nobel Prize, da-da-da-da-da. And nothing about this entire scientific process is about me, 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 despite all the me, 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 me of all the mostly white old men in this talk. Ultimately, science is social. And the reason why equity in physics is important to me, there are all sorts of reasons, but the reason I want to highlight here is about the scientific enterprise. How many people here saw Oppenheimer? Okay, that's the most responses yet. So there was a character in Oppenheimer, Vannevar Bush. This is him on the right. For the most part, he was a good guy. The only picture I could find is him shaking hands with the bad guy, Strauss. Vannevar Bush is widely recognized to be the person who spearheaded the National Science Foundation. The National Science Foundation is, in my opinion, perhaps the greatest force in the history of humankind for basic research. And the asterisk is, I am currently funded by the National Science Foundation. But I think it is true. I think it is true. And this is the report in 1945. 1945, we are still in the war. The Manhattan Project is happening. Oppenheimer is happening. And he writes this report to the president seeking funding for civilian-led basic research. Not how do we build more bombs, but how do we understand the cosmos. And in this report, he quotes a chemist. In every section where the word science may be properly applied, the limiting factor is human. This is still true today. You remember the quote in Oppenheimer where they were talking about what the stakes were. The Germans are building the bomb. The Americans, this is a relatively new, young scientific community with physicists who were barely learning quantum mechanics. What chance do they have? And Oppenheimer speculates the chance that we have is anti-Semitism in Europe. The fact that we are diverse, right? That was part of the story of Oppenheimer. And so the limiting factor is a human one. Inasmuch as I am excited that now is the time to study dark matter, because of this, because of this, because of this, because of this, like all these great things, we have all of the cool toys to really attack this problem. The most valuable thing that we have, and that we are still desperately in need of, is this. And that's why it matters to me. If only a fraction of our society gets to send the ones who are most passionate and willing to build the skills and do the practice and apply it to this field, then we are missing out. Okay, let's zoom back out one last time. Why are we doing this? Maybe you've seen pictures like this. Here is our cosmic history. About 13 billion years ago, something which looked like a quantum fluctuation rapidly expanded and produced our universe. In the early universe, things were very hot. You produced lots of stuff. A lot of that stuff was dark matter. As the universe cooled down, the dark matter also cooled down and fell into this structure, this purple goop over here. It looks like a sponge or neurons or something like that. And if we zoom in, that dark matter formed these filaments, and where those filaments intersected, they had overdensities of dark matter, which had lots of gravitational pull. And in addition to pulling more dark matter to create more density, they pulled together these stray minority of atoms, hydrogen atoms that were just floating around. And those hydrogen atoms came together. They lost their angular momentum. They collapsed. They'd form things like stars. Some of those stars would go supernova and form heavy elements. And a few million years, and we have things like the solar system. Some lucky amino acids produce life, and here we are. And if we had a little bit more dark matter, within the experimental uncertainty, if there's 1% more dark matter than we think, this universe will go on and crunch back in on itself long after we're all gone. If we had a little tiny bit less dark matter, 1% less, the universe would likely expand forever. And when I think about that, when I think about these stakes, we are this fish. In fact, you know what? This is the Copernican principle. Not only is the Earth not in the center of the solar system, our solar system is not in the center of the galaxy. Our galaxy is not particularly important compared to the other galaxies in our cluster, and there are a whole bunch of these galaxy clusters all over the place. And by the way, all of the stuff that we can see is a tiny fraction of the actual stuff that is forming the substructure of the universe. So one last painting, the one that I often think about when I think about this cosmic context. This is, where do we come from? What are we? Where are we going? From Gauguin. So where do we come from? Dark matter is a big part of that story. Where are we going? Dark matter is a big part of that story. What are we? We're the fish that are swimming in the ocean of dark matter, that are discovering water for the first time. And it's amazing that we're doing this. How we do this, and the fact that we are able to get together as a human civilization to do this is amazing. And I think that's a big part of our cosmology. All right, thank you very much.